Hello again. As you can see, I've by the title, I've managed to disguise my intentions again with a hypothetical Jeopardy. Jeopardy being the television game show hosted by what's his name? What was his name? What do they call this? Alex Trebek. Actually, I know somebody who's been on that show. Well, I used to know a guy who's been on that show. I don't even know if he's still around. But he was the highest money-earning player of that show before they changed the rules. Apparently, this guy called Mark Warren, and but I don't know if you read the blurbs that I put on each video. I often spend a long time on those blurbs, and I don't know if anyone reads them. But I wasn't kidding. You can see that after chariot racing, there's a pentathlon, meaning a grouping of five events, including exhaustively, including wrestling, Stadion, I don't know what that is, and nor does anybody else, long jump, our thing, Javelin throw, and Discus. The latter three were not separate, so these were all one event. In the chariot racing, it was not the rider, but the owner of the chariot team was considered the competitor. So that's like Formula One racing, I guess, today, right? It's not the driver who wins; it's the team that wins. So not much just changed in that regard. So that was the first thing. I just went to check and see if it works as advertised, and I decided to use Woo Test for fun, which doesn't normally come with a console. Under debug, we get a console, and I can select one or another of these tests by changing this value here. So for the long jump test, I run up to here. Now, I haven't really looked online. So we have a console. Well, in this test, first I had just one, but now you'll notice that I've got two what they call jump buff. And a jump buff is a JB type jump buff of JB length. So an array of these, which are ints. Not surprisingly, since they represent, oh my goodness, here it is. I was trying to figure out what this structure is. Let's see now. This is what I came up with. Let me grab this. I want to be here. No. Here. EBP, EBX, DI, SI. I was right for those. I'm off by one. Here. EBP, EBX, DI, SI. I was right for those. I'm off by one. EBP, EBX, DI, SI. I was right for those. I'm off by one. EBP, EBX, DI, SI. I was right for those. I'm off by one. EBP, EBX, DI, SI. I was right for those. I'm off by one. EBP, EBX, DI, SI. I was right for those. I'm off by one. EBP, EBX, DI, SI. I was right for those. I'm off by one. EBP, EBX, DI, SI. I was right for those. I'm off by one. EBP, EBX, DI, SI. I was right for those. I'm off by one. EBP, EBX, DI, SI. I was right for those. I'm off by one. EBP, EBX, DI, SI. I was right for those. I'm off by one. EBP, EBX, DI, SI. I was right for those. I'm off by one. EBP, EBX, DI, SI. I was right for those. I'm off by one. EBP, EBX, DI, SI. I was right for those. I'm off by one. EBP, EBX, DI, SI. I was right for This, it says ESP. Oh, unknown, yeah. Yeah, so that's ESP. Well, I'll just use this thing. IP. Now this says registration. I thought it worked out that it was SP. And that's not true. This is ESP. Some were the same, and so. Registry. Don't know what that is. Tri-level, I see. This was called, in the disassembly, there was a variable name, symbol name called count. It wasn't called tri-level. And I thought this one was ECX. Well, it might be that that's where this cookie is stored. But it's not meant to be CX isn't in the picture. Now, unwind func. Let's see, a function pointer. Why am I even copying this? So we have a struct. No. Okay, so I'll have to just change my printout. I could, no, I don't have to use the same name. You can put capitals. Was I calling it before? Tag context. And then context. Alright. Unwind data, I don't know about that. Now, see what I was doing was after the set jump, filled up one of these jump buffs, and I was printing them out. So I want these to be caps. BP, IP, SP. I don't know about CX. DI and SI. I have. B. How many registers? 1, 2, 3, 4, 5, 6. 6. Are they the same? BX. Yes. SI, DI, SP, IP, BP. That's the same. So what I was calling count is this, I think. It's the nth try, I suppose. And now I can print these up, but I don't know the meaning. So I'll print them out anyway. Now this is going to be a pointer. It's an int, but an int is a pointer in Win32. Unwind No. Funk, yeah. Okay. And unwind data. I'm not sure how best to print that. 6 bytes. I messed up my alignment here. Oops. It's just a number. Funk. Unwind. Funk. Not done. Funk. Try level. And that leaves this. Which I suppose we could just print it out this way. Need to be fancy. And use copy paste in this case. Now you know I'm against copy and paste, but sometimes that's exactly what you need. If I put that there, no it won't. We won't put them all on the stack, it'll put a reference. Unless I made it a struct. Which is the only way to pass an array to a function. You gotta make a struct. Okay, now I should turn this into a function. Now here, now this is C. I don't know what I'm allowed to do. Can I make an inline function? Print context, taking this thing. There are no references, but you can just say that. That's the same as passing a reference. Well, it might make a copy. No, it'll make a copy in this case. It should, which is fine. And then I just want to do this. You never know, but I want it to be C. I could, I don't know about casting. Casting probably doesn't work either. Alright, now I have that in several places. Let me pause this and clean it. Okay, all done. I had to pass it as a pointer. It's the only way to do it apparently. But whatever. So now I made a new file for Leave utilities. Should they come up? Another might come up. So now this here is just printing out what gets filled into this jump box. Now I just declare one of those more meaningful things that is a union of the jump buff and what it means. And I can pass a pointer to one of those to this print thing, and it'll print out the current context at this line immediately after the set jump call. Okay, and that's where we are. Now I can go to test the initial task, foo 0. Now see what I've done is I did it again because I wanted to see if that counter would go up. So instead of doing this, why don't I just raise exception. Why don't I call this foo 1? I should call this raise exception. Raise random exception. Oh, I see. Okay, so instead of what I've got, I'll just do alright, and any old number. No, that's just like the one in the article. Part 1 of that article gives this example. That's where I took it from. Instead of using a single letter, I don't typically use a single letter for a struct. Maybe that's how they did it in 1999, but not anymore. Raise exception. What's raise exception? That does a long. Oh yes, that's true. I made up my own raise exception. I've got to pass in the jump buff. It takes a jump buff and an integer exception. The reason is because I wanted to try jumping to randomly one or the other from the same function. So I made that parameter. Now this here is this buffer. So this contains the context, whatever it was at the point of the set jump, and that should be restored. And 1, 2, 3 will be the return value of this set jump, and I'm storing that in pirec. Now, let's see, raise exception calls long jump with a jump buff marker and an exception number, and long jump is documented in the help. Of course, it's documented in the help, by the way. What in there? Never mind. Long jump. Be careful, blah, blah, blah. Restore stack environment and execution locale. Alright, that's all it does. So, start from woo test. That's giving an unreachable code warning. That's okay. We know that it was complaining about this line, and it's true, it's unreachable. Nothing would follow a long jump. So here's our return value. So I'm just going to step over it right now. I'll show you it working. Now I'm just copying everything from this, which is a great big array, into here, which is very meaningful, more meaningful view. This is what the registers were. These registers at the time of the set jump. There is no unwind func. There's a cookie thing. I don't know what it means. Tri-level, I assume, means that if I'm not sure, because if I do it twice, it doesn't go up. And I would have thought that if I'm already, oh, I see, tri-level maybe on this. No, can be. Well, maybe yeah, it could be. It could be that if you call this function recursively, I wouldn't dare to even think about it. But let's see what it prints out. No unwind func, no unwind data. So I suppose if we had an unwind func, whatever it does, these 6 bytes would be the 6 bytes required for that function. Now it could be, because we've only got bx, right? And what's missing is ax, cx, s, sp, cx, dx we don't have, so ax, cx, dx, that's 3. And flags, we don't have flags, that's 4. And then there's these stack things, but you would only need 2. The only 2 of any importance are this one, fs, and any one of these code segments. Not the same as. Okay, so you would need 3 for the segments. They're really 3 values. I'll get back to this FS eventually. This has to do with structured exception handling specifically. This is the code segment. I don't know why it's given. Oh, I know why it's given. The reason this has a different value doesn't mean that it's not still a flat memory model. It's just that in a protected mode environment, these segment numbers point to entries in a table that have information pertaining to like security rights and so on. Is it read-only? Is it executable? And so on. And so this DS might be read-write data, right? CS is certainly read-only, execute. Stack is like data. But I know that there's some read-only data stuff, so I don't know how that works exactly. There are more and more tables. Anyway, so now according to theory, if I just step into this, the long jump should take me with value 123 right back to where we started. It seemed to work before. Let's try it again. Just quit. I know it's going to come back here. Alright. Let's see where it goes. Now you're going to step over this bit. This is the part that you have to decipher. But eventually it's going to sort out an address and call it here. Not yet. Looks like it's returning to it. Here we are, back here where we started. I think the last thing was a return, wasn't it? It's doing it differently this time. Just gotta make sure I don't step over. No on 1, push 0, AX something. That's certainly the where we're going. So that's code. I don't know what that function does. EX. Maybe that's just restoring the registers. Compare EAX to 1. And carry. SP. Now it's restoring the stack pointer. Adding 4 to that. Now it's just a jump. I see. It just jumped here. Okay. It never returned. There's epilogue code in that function, but it's unreachable. Whatever it was. Can't see it, can we? I'm curious, but I want to see that again. Just wondering if that's there on purpose or what. Here's the restoring. Stack pointer gets turned into, now there's, unless something can jump to here, there must be a jump to the EEF5 somewhere. Otherwise that code is completely useless. But I mean, the compiler itself, when it makes these functions, it always adds an enter and a leave for everything, right? If it's just declared as a regular function, it's going to put this at the beginning and this at the end, even if you don't use it. So it might be that this is unreachable code. There's nothing jumps here. Okay, so now the point is, we've just called a function and it's set the scenario up in such a way that when we restore where the It's a C call, so we're cleaning up. We're doing our, after we clean up our stack. Okay. EAX now contains the value 1, 2, 3, which is not 0. So that takes us to here. And we print it out. Exception 1, 2, 3 was raised. Okay, so it worked, just as advertised. Okay, now what I did was, instead of raising exception for curiosity, I made up another function called this. Doesn't take any arguments. And it does another set jump with another marker. Okay, and print it out as before. And then it calls yet another function. And this function generates a random number for the exception. And depending on whether this is odd or even, it goes to one or another of these labels. Oh, and also, if I end up back here on this one, so if this function jumps to mark 1, then that puts us here, and then I add 20 to the exception, just so that when we raise it, we'll see a different value from what was initially set. I haven't learned anything yet. I'm just seeing that it works. It might not do it first time. No, we got it first time. So we're in foo 1, and we're about to raise 11097. We raise that exception. And now we're in long jump test. That's this one. So we ended up back here by random chance, and we added 20. So that's the last one. We ended up in foo 0 here, and then we added 20 and raised exception to go to mark 0, back up to this one, which then entered its exception code and printed out the result. If I run it again, this time I only got 2, so it's just a little randomness. Now I'm curious about this try level, but let's see how my time is. Okay, let's see how it sets it up. Let's see. The interesting part, right, is that what happens in this, how this gets restored, and how this gets set, right? Well, this isn't even very you can guess what this is going to look like. Let's just have a look. Try and work it out. Okay. So we have to call. First we're pushing 0. Why are we pushing 0? Because we want to make a comparison. And then offset that. Now it could be that set jump has a secret second argument, Okay. Because this is pushing two things, and with only one thing, apparently, one argument that this function takes. We'll find out in a minute. It doesn't say. And notice there's no prologue or anything code. This is all written in assembler. Well, that's memset. Okay. So now we've just executed a call, right? Now where can I draw a picture? Edit? Notepad? So the stack, what we currently have is we just did a call, so the stack pointer is pointing at the return address, right? Because we did a call and nothing else. And a 0 was pushed, so there's a 0, but the 0 was pushed first, so there's a 0 here, and here at SP plus 4 is the address of the struct, which was called LJ mark 0. And this is 8. For some reason there's a 0 there. Alright. So now into dx is going according to this. So edx step 1. Okay. No. Yeah, that's it, step 1. And now into a bracket dx. Alright. We're placing the value of EBP. How does that jive with our structure? That is the first thing that's supposed to go in the structure. Okay, and then DI with BX. So BX, DI, SI, ESP. So, and EIP, well, I don't know how that's going to work. So all the way up to ESP. It keeps adding one more D word. And it's exactly according to this. Not so complicated to understand, right? Oops. This one's correct. BP, BX, DI, SI, ESP. Now, how does it do that? Oh, we haven't touched ESP, right? But we've made a call. So this is not the ESP that on the line when we called this function. When we called this, we pushed two things on the stack, and then we called this, and so this ESP is off from what it was before the call by 8 bytes, according to theory. So ESP at call plus 8. That's okay, that's probably something it just subtracts that off later. Now what are we doing? Bracket ESP points at the return address, right? Okay. Now I think we're familiar with this sort of thing. So we put into EAX bracket ESP, and that's pointing at the return address. And now we're putting that value as the next one in the table, which is supposed to be EIP, but it's off by what is it off by? The return address is a call is 5 bytes, so it's 5 bytes off. But that's okay, it can be added later on. Well, the address of the call. Right? Because if you recall, a call is E8 or something, and then there's a D word. Something like this, right? That's what a call instruction looks like. And the return address it's here. And ESP is pointing here. So to get the address where the call was made, we'd have to subtract 8 from this value, but whatever. So now we're putting that AX as the next value of the table. Now all this can be worked out in reverse order. So now what's this? The next thing, that's not the next thing. The next thing would be 18, and this is 20. We just did that one. Now I keep screwing up on these. 14. Plus 4 is 18. That's 1, 2, plus 1c, and then another 4 is 20. So that's the third. After this, jump ahead 3. This plus 12, I think, is that right? 12 decimal, which is C. See, I was right. So to get to 20, we would have to add 12, which is 3 times 4. So that's 1, 2, that's the cookie, I see. So into 20 goes cookie. Which is a magic number, special fixed value. The next is a 0 and 1 point we have. All making sense so far? And okay, now this FS thing has to do with structured exception handling. And we're putting that, now that's something that I got to get to later on. You see, this segment is a special segment specifically for structured exceptions. The processor invents this segment for us. And in the case of, for instance, a crash or whatever, the processor, I forget how it works, but somehow or other, the processor, you can set up a callback or something, and it'll call your callback, and then you build a chain through this FS. This whole thing, starting at 0, becomes a linked list of callbacks. The SEH chain, structured exception handling chain. And what we're doing is we're extracting the 0th element, putting that into EAX, which I imagine is going to be 0, because we're not doing anything. No, it has a value. Now, was that the one? We don't know. Oh, it should be, that's certainly a stack pointer. What's our stack pointer? Can I look at these? It's too late, probably. Which one was stack? The 5th one. It's on there, it's in decimal. This doesn't say anything. But that certainly looks like a stack number. And now we're placing that into 18. dx plus 18, which is supposed to be maybe the try. Oh, registration. 14 was EIP. That's true. Okay, so registration. In one word, we could say. Okay. Now, forget about. Don't worry too much about this. We'll get to it. And this does have a value. I don't know why it's got a value. And now we're comparing AX with minus 1. I haven't done it yet. Well, it doesn't matter. AX was not minus 1. About an actual value. Minus 1 must mean something. If it's not minus 1, jump to get count. That's why I called that thing count. CX is SP plus 8. We modified SP? No. Oh, that was that thing that was pushed. The first thing that was pushed, it should be 0. It is 0. Okay. Remember, a 0 was pushed. Is it 0? Yes. Go to default try level. Into AX goes. AX was the thing we got from that weirdo address. Happens to be the value 1. I see. So whatever's that FS0 is a pointer to something else, which I suppose probably tells us how many right, the current level of tries. There's try and catch, or whatever, something like that. Anyway, and now we're placing that where it belongs on the table, and we're done. So set AX to 0 always, and return. Okay, now so this thing always gives 0 the first time you run it. It's during the setup phase. And this is my bit I added here. And now we're ready to go and run through the next part. So I'm going to leave this in this state, and that'll be the next video, I guess. Okay, see you next time.